Welcome. You have found a quiet place in the middle of everything that is happening. Whatever is on your mind right now, whatever you were doing just before this moment, you can set it aside. There is nothing you need to decide right now. There is nowhere you need to be. Tonight, we are going to travel somewhere very far away. Not in any hurried way. Not with urgency or excitement. We are going to move slowly, as one moves through still water, gently without disturbing anything. What we are going to explore tonight is one of the most remarkable objects in the observable universe. It goes by several names. Scientists call it NGC 7293. Those who catalog the sky call it a planetary nebula. But most people who have seen it through photographs taken by the great observatories of our time simply call it the Eye of God. It is also known as the Helix Nebula. It sits in the southern constellation of Aquarius. It is the closest planetary nebula to Earth that we know of, close of course in cosmic terms, which means it is still roughly 650 light-years away. That is a distance so large that no number we place beside it will carry full meaning. Light, which travels at approximately 300,000 kilometers every second, takes 650 years to cross from there to here. The light reaching our instruments right now left that nebula sometime in the 14th century. We will spend this time together moving through what is known about this object, what it is made of, how it came to be, what it looks like up close, and what it tells us about the nature of stars and time. There is no rush. The Helix Nebula has been expanding slowly through space for thousands of years. It will still be there whenever you return to this thought. Before we begin, a gentle reminder. If you are watching or listening to this on YouTube, and the words we share tonight bring you some peace, some quiet, then consider taking a moment to like this video and to subscribe to Sleepy Scientist. It helps this channel continue bringing these long, calm journeys to more people who need them. That is all that is ever asked of you here. And now we begin. Close your eyes if you like, or simply let your gaze soften. Allow the information to come to you without effort. You do not need to remember any of this. It is simply here, like the sound of rain on a roof, offering something to follow. We start at the beginning, or at least one kind of beginning. The Helix Nebula is a planetary nebula. That term, planetary nebula, is a historical accident of language. When astronomers in the 18th century first observed such objects through their early telescopes, the soft, rounded, glowing shapes reminded them of the disks of planets like Uranus or Neptune. They were not planets and had nothing to do with planets. But the name remained. A planetary nebula is the final chapter of a certain kind of star's life. Not the very largest stars and not the very smallest. Stars in a middle range, stars like our own sun or somewhat larger, end their lives by expanding outward into enormous shells of gas and light. What we see when we look at the Helix Nebula is that shell. It is the outer layers of a star that no longer exists as it once was, cast off into space and still drifting outward, illuminated by the remnant at its center. The Helix Nebula is large. In terms of apparent size in the sky, it spans an area roughly equal to half the diameter of a full moon as seen from Earth. That may not sound enormous, but for an object made of diffuse gas drifting in the space between stars, it is remarkable. It is, in fact, one of the largest planetary nebulae visible in our sky, partly because it is one of the closest. Its actual physical diameter, if you were to draw a line from one edge to the other, is somewhere around 2 to 3 light-years. That means if you placed it at the center of our own solar system, its outer edge would extend well past the Oort cloud, the distant, icy shell that marks the outermost boundary of the sun's gravitational influence. The structure of the helix is not simple. It is not a single uniform bubble of gas. When examined closely, it reveals layers. It reveals filaments. It reveals 2 distinct rings, nested one inside the other, oriented slightly differently, creating the impression of a complex and multi-layered form. There are thousands of elongated features within the nebula that astronomers call cometary knots. Structures shaped somewhat like teardrops, each one roughly the size of our entire solar system, pointing away from the central star like compass needles pointing outward from a center. The colors that appear in photographs of the Helix Nebula are real, in the sense that they correspond to real light emissions, though the specific hues used in images are often mapped from wavelengths that our eyes cannot directly see. The blue-green inner regions glow in the light of ionized oxygen and helium. The outer red ring glows in the light of ionized hydrogen and nitrogen. These colors tell us something about the temperature and composition of the gas at different distances from the central remnant. The central star, the object that remains where a full, living star once stood, is now what astronomers call a white dwarf. It is a dense, hot, slowly cooling body, not much larger than Earth in physical size, but carrying within it roughly 60% of the mass of our Sun. It radiates intensely in ultraviolet light, and it is this radiation that causes the surrounding gas to glow. The Helix Nebula is, in a quiet and factual sense, a picture of our own future. Our Sun is expected to pass through this same phase several billion years from now. What we observe here, this great ring of expelled gas, this slowly cooling remnant at the center, is a process that applies to our own star. Not urgently, not soon in any human sense. But the process is real, and it has been happening here in this nebula for the past 10 to 12,000 years. We can take that in slowly. The Helix Nebula occupies a position in the constellation Aquarius. Aquarius is one of the oldest recognized constellations. It was catalogued by the Greek astronomer Ptolemy in the 2nd century of the Common Era, though its origins stretch further back through Babylonian astronomy, where it was associated with the god Ea, who was often depicted carrying an overflowing water jug. The constellation is large, one of the larger figures in the sky, and lies in a region of the celestial sphere sometimes called the Sea, because it sits near other water-themed constellations like Pisces, Capricornus, and Eridanus. Finding Aquarius requires a reasonably dark sky and some patience. In the northern hemisphere, it is a summer and autumn constellation, visible in the evening from roughly August through October. For observers in the southern hemisphere, it rides higher in the sky and is easier to see. Within Aquarius, the Helix Nebula is located at coordinates that place it near the border with the constellation Piscis Austrinus. Its precise position is approximately 22 hours 29 minutes right ascension and minus 20 degrees 50 minutes declination. A coordinate system that describes positions on the celestial sphere much as latitude and longitude describe positions on Earth. Visually, the nebula is challenging to observe with the naked eye. Under excellent conditions, it may be barely detectable, but it requires a wide-field view because its light is spread across a relatively large area of sky. Paradoxically, the helix can be more difficult to see through a small telescope than through good binoculars, because a telescope concentrates light into a smaller field and can make a large, diffuse object harder to resolve. Wide-field binoculars on a very dark night can reveal a faint, soft glow in the appropriate location. The first recorded observation of the Helix Nebula was made in the early 19th century. The German-Polish astronomer Carl Ludwig Harding is credited with its discovery around 1824. Harding was a careful observer who spent much of his career at the Göttingen Observatory. He catalogued the nebula as one of many faint, extended objects that accumulated in the growing inventories of deep sky objects during that period. Later in the 19th century, the American astronomer Edward Emerson Barnard, known for his exceptional visual acuity and his exhaustive surveys of faint sky objects, also observed and noted the nebula. But it was the 20th century, with the development of photographic astronomy and then digital imaging, that truly revealed the helix in its complexity. Some of the most detailed images of the Helix Nebula were produced by the Hubble Space Telescope, along with ground-based observatories equipped with wide-field cameras. These images, particularly a composite released in the early 2000s, circulated widely across the internet. The photograph showed a vast, layered ring of glowing gas surrounding a central blue-white point of light, an image that, to many observers, suggested a vast eye looking back at them from the darkness. That is where the popular name comes from, the Eye of God. It is not a formal scientific designation, and astronomers do not use it in their papers, but it has become the most widely recognized name for this object in popular culture. There is something in the symmetry and the central point of light that the human visual system maps onto the form of an eye, pupils, iris, surrounding structure. It is a pareidolia in the strict sense, but it is a memorable and striking one, and it has brought the Helix Nebula to the attention of millions of people who might otherwise never have encountered it. The distance to the Helix Nebula has been refined over the decades. Current estimates from parallax measurements and modeling place it at approximately 655 light-years, Some estimates suggest up to 700 light-years, depending on the methodology used. This places it as the nearest well-studied planetary nebula to Earth, making it one of the most important objects of its type for scientific study. At that distance, the nebula has an actual diameter of approximately 2 to 3 light-years for its main structure, with some outer components extending further. It is, in the language of deep sky observers, an object of great angular extent and moderate surface brightness, meaning it covers a large area but has its light spread thinly across that area. We sit here on this planet and we look in that direction, and the light that reaches us tonight has been traveling since long before any living person's grandmother was born. When astronomers began to study the Helix Nebula in earnest, particularly as detector technology improved through the latter decades of the 20th century, they found that its structure was considerably more complex than a simple ring or bubble. The most prominent feature, visible even in modest images, is the main ring, an outer torus of gas glowing in reddish light, corresponding mostly to ionized hydrogen. This ring is not a flat disk. It is better described as a torus or a donut shape seen at a slight angle close to face-on but not perfectly so. The angle of inclination from our line of sight is estimated at around 37 degrees. So we are looking somewhat down into the structure, rather than purely sideways through it. Inside this outer ring sits an inner region that glows more blue-green, dominated by emissions from ionized oxygen and helium at higher temperatures. The inner region corresponds to gas that is closer to the central star and therefore exposed to more intense ultraviolet radiation. But what makes the helix particularly interesting, even among planetary nebulae, are the structures within it known as cometary knots. The cometary knots of the Helix Nebula are dense, compact concentrations of gas and dust, each with a bright head and an extended tail pointing away from the central white dwarf. They are called cometary because of their superficial resemblance to comets, but they are vastly larger. Each cometary knot is roughly 100 astronomical units across at its head, meaning if you set one end at our Sun, the head alone would extend to about 2.5 times the distance to Pluto. The tails can be up to 1,000 astronomical units long. There are approximately 20,000 such knots in the Helix Nebula. They are distributed primarily throughout the main ring structure. The tails all point radially outward from the central star, which tells astronomers that they are being shaped by the radiation and stellar wind from that central source. What causes them? The current understanding is that they form through an instability that occurs when the fast, hot stellar wind from the central white dwarf overtakes and interacts with the slower, denser gas that was expelled earlier in the star's life. Where the two flows meet, density irregularities grow. Dense clumps that happen to form at these boundaries get sculpted by the radiation into the characteristic head and tail forms we observe. The knots are not static. They are moving. Their heads are being photoionized and ablated, a slow erosive process driven by ultraviolet radiation, while their dense interiors may, in some cases, preserve material for much longer timescales. There is also evidence that the Helix Nebula has at least 2 distinct outflow episodes, each oriented slightly differently. The inner disk and the outer ring do not share exactly the same orientation in space. They are tilted relative to each other. This has led to models suggesting the central star may have been affected by a companion body, or that the star's rotation axis changed over time, or that the outflows occurred at different epochs when the star's orientation was different. One of the most widely discussed features of the Helix Nebula's geometry is what happens at its center. The innermost region, surrounding the white dwarf at very close distances, shows an inner disk or inner ring that is oriented differently from the main torus. Some models describe the whole structure as a combination of a roughly equatorial torus and a set of bipolar or multipolar outflows, producing the layered appearance we observe. There is also an outer halo, a faint, extended component reaching to roughly 4 light-years in diameter, detectable only in very deep images. This halo likely represents material expelled even earlier in the star's evolution, before the main nebula-forming events took place. The overall impression is of a structure that evolved over thousands of years, in multiple episodes, and that continues to evolve, slowly expanding, slowly cooling, slowly dispersing into the broader interstellar medium. In a few tens of thousands of years, a short time astronomically speaking, the nebula will have expanded and thinned to the point where it is no longer visible as a coherent structure. The material will have mixed back into the interstellar gas, and the white dwarf will continue its long, slow cooling, alone. But right now, at this particular moment in that long process, the structure is visible and structured, and in some ways beautiful in its complexity. To understand the Helix Nebula, it helps to understand the kind of star that made it. The star at the center of the helix, the one now reduced to a white dwarf, was, in its earlier life, a star broadly similar to our Sun, though probably somewhat more massive. Estimates of its original mass range from roughly 2 to 4 times the mass of the Sun. Stars in this mass range follow a predictable sequence of life stages, governed by the physics of nuclear fusion and gravity. A star begins its life as a collapsing cloud of hydrogen gas. Gravity draws the cloud inward. As the cloud contracts, it heats. When the core reaches temperatures of around 10 million degrees Celsius, hydrogen fusion begins. Protons are forced together to create helium nuclei, releasing enormous amounts of energy in the process. This energy creates outward pressure that counteracts the inward pull of gravity, and the star reaches a stable balance. This phase is called the main sequence. Our Sun has been on the main sequence for approximately 4.6 billion years. A star with 2 or 3 times the Sun's mass burns through its hydrogen more quickly, in hundreds of millions of years rather than billions. The timescale depends sensitively on mass. Heavier stars burn brighter and faster. When the hydrogen in a star's core is exhausted, the core contracts under gravity while the outer layers expand enormously. The star becomes a red giant. In this phase, the star can swell to many times its original size, in some cases expanding to hundreds of times its previous radius. The outer atmosphere becomes loosely bound, puffed outward by thermal pressure and radiation. During the red giant phase, stars shed material into space. There is a steady stellar wind, a flow of particles and gas leaving the star's outer layers, and as the star pulses and expands, this mass loss accelerates. Over thousands and millions of years, the star can shed a substantial fraction of its original mass this way. As the star evolves further, it enters a phase called the asymptotic giant branch, or AGB. This is a particularly unstable phase, characterized by alternating hydrogen and helium shell burning, and by strong pulsations. The mass loss during the AGB phase is significant. The star can lose material at rates far higher than during earlier red giant phases. The expelled material forms a thick, dusty envelope around the star. This is sometimes called a circumstellar envelope, and it can obscure the central star entirely in visible light, though it glows in infrared wavelengths. Eventually, the star's outer layers are shed almost entirely. What remains is the core, the white dwarf, exposed and radiating at extremely high temperatures. The white dwarf is composed mostly of carbon and oxygen, the ash products of helium fusion in the star's interior. It is no longer generating energy through fusion. It is simply radiating away the heat stored in its dense interior, and it will continue to do so for billions of years. The expelled outer layers, now cast into the surrounding space, are illuminated by the intense ultraviolet radiation from the newly exposed white dwarf. They glow. We call the result a planetary nebula. The Helix Nebula's central white dwarf is classified as a star of spectral type Tau, an extremely hot, hydrogen atmosphere white dwarf with some helium present. Its surface temperature is estimated at around 100,000 to 120,000 Kelvin, far hotter than our Sun's surface temperature of about 5,800 Kelvin. Over billions of years, this white dwarf will cool. The process is very slow. White dwarfs lose heat gradually, and even after a billion years, they may still glow dimly. The surrounding nebula is estimated to have an age of approximately 10,000 to 12,000 years, measured from the time the main mass loss event began forming the current structure. That is a relatively short time in astronomical terms, younger than the oldest known human civilizations, and yet in those 10,000 years, the nebula has expanded to a diameter of over 2 light-years. The expansion velocity of the Helix Nebula's gas is estimated at around 31 kilometers per second for the main ring. This is not a violent explosion. It is more like a very slow, steady exhalation. At that speed, however, over 10,000 years, the gas has traveled a very large distance. At the very center of the Helix Nebula, there is a star. It does not look like the stars we see in the night sky. It is very small, roughly comparable to Earth in physical diameter, perhaps slightly larger. It is very dense. A teaspoon of its material would weigh many tons. It has no ongoing fusion at its core. It is not creating new energy in the way that main sequence stars do. What it is doing is cooling. White dwarfs are sometimes described as stellar embers. They are the remnants of nuclear fires that have gone out, left to radiate away the residual heat stored in their interiors over timescales that stretch into the far future. The white dwarf at the center of the helix will not change dramatically on any timescale that has meaning to human experience. The particular white dwarf here is identified in catalogs as WD 2226 to 210, or sometimes simply as the central star of NGC 7293. It has a surface temperature of roughly 100,000 to 120,000 Kelvin. At these temperatures, the dominant output is ultraviolet and soft X-ray radiation, wavelengths of light that our eyes cannot see, but that instruments in space can detect. This ultraviolet radiation is what powers the nebula's glow. As it travels outward through the surrounding gas, it strips electrons from atoms of hydrogen, helium, oxygen, and nitrogen. When those electrons recombine with their parent atoms, they emit light at specific characteristic wavelengths, a process called nebular emission. The colors we see in images of the helix are the signatures of these recombination events. The Helix Nebula's central white dwarf has been detected in X-rays by orbiting telescopes. The X-ray emission comes from the hot surface of the dwarf itself, and possibly also from a hot wind still being shed from the remnant. It has also been detected in far ultraviolet light by space-based instruments designed specifically to observe at these wavelengths. At the very center of the Helix Nebula, there is a star. It does not look like the stars we see in the night sky. It is very small, roughly comparable to Earth in physical diameter, perhaps slightly larger. It is very dense. A teaspoon of its material would weigh many tons. It has no ongoing fusion at its core. It is not creating new energy in the way that main sequence stars do. What it is doing is cooling. White dwarfs are sometimes described as stellar embers. They are the remnants of nuclear fires that have gone out, left to radiate away the residual heat stored in their interiors over timescales that stretch into the far future. The white dwarf at the center of the helix will not change dramatically on any timescale that has meaning to human experience. The particular white dwarf here is identified in catalogs as WD 2226 to 210, or sometimes simply as the central star of NGC 7293. It has a surface temperature of roughly 100,000 to 120,000 Kelvin. At these temperatures, the dominant output is ultraviolet and soft X-ray radiation, wavelengths of light that our eyes cannot see, but that instruments in space can detect. This ultraviolet radiation is what powers the nebula's glow. As it travels outward through the surrounding gas, it strips electrons from atoms of hydrogen, helium, oxygen, and nitrogen. When those electrons recombine with their parent atoms, they emit light at specific characteristic wavelengths, a process called nebular emission. The colors we see in images of the helix are the signatures of these recombination events. The Helix Nebula's central white dwarf has been detected in X-rays by orbiting telescopes. The X-ray emission comes from the hot surface of the dwarf itself, and possibly also from a hot wind still being shed from the remnant. It has also been detected in far ultraviolet light by space-based instruments designed specifically to observe at these wavelengths. One notable observation involves what appears to be an infrared excess around the central white dwarf, a slight surplus of infrared radiation beyond what would be expected from the star alone. One interpretation of this finding is that there is a disk of dust around the white dwarf, possibly the debris of asteroids or comets that survived the star's red giant phase and were subsequently disrupted as they passed close to the dense remnant. If this interpretation is correct, it would be a quiet and distant remnant of a planetary system, the ash of worlds that may have once orbited the original star. This is speculative, and the evidence is debated in the scientific literature. But it is a thought that carries a certain resonance, the possibility that somewhere within the glowing structure of the Helix Nebula, there are the remains of rocky bodies that once orbited a star in ways not entirely unlike the way Earth orbits the Sun. The white dwarf will cool over the next few billion years. Eventually, it will cool to the point where it is no longer luminous in any wavelength we can practically observe, becoming what is theoretically called a black dwarf. However, the current age of the universe is not yet old enough for any white dwarf to have cooled to this state. The universe is simply not old enough. Every white dwarf that has ever formed is still, in principle, detectable as a dim but warm remnant. In the meantime, the central star of the Helix Nebula continues its slow radiation, illuminating the surrounding gas, creating the glow that we photograph and study from 650 light-years away. The images of the Helix Nebula that circulate most widely, the ones sometimes labeled with the name Eye of God, are composite images, assembled from multiple exposures taken at different wavelengths of light. This is worth understanding because it shapes how we interpret what we see. Visible light occupies only a narrow band of the full electromagnetic spectrum, a range of wavelengths that human eyes can detect, spanning from roughly 380 to 700 nanometers. Astronomy, however, observes across a far wider range: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Different physical processes emit light at different wavelengths, and to understand what is happening in a nebula, astronomers observe across as many of these wavelengths as possible. In the case of the helix, much of the interesting emission comes in wavelengths that are at or near the edge of visible light or just beyond it. Hydrogen alpha emission, one of the brightest lines from ionized hydrogen, falls at 656 nanometers, deep red, visible to human eyes, though the specific wavelength is a bit redder than what cameras naturally render. The oxygen 3 doublet, produced by doubly ionized oxygen, falls at around 500 nanometers, a blue-green color within the visible range. When assembling images for public release, astronomers and image processors make choices about which wavelengths to represent in which colors, and how to balance the exposures. The famous Hubble images of the helix used a combination of ground-based wide-field imaging and Hubble's sharper but narrower field, and assigned colors in ways that represent the relative intensities of different emission lines while also being visually informative. The result is an image that shows the outer red ring as hydrogen-dominated and the inner regions as oxygen-dominated, which is physically accurate and also corresponds to the temperature gradient in the nebula. Gas close to the hot white dwarf is more thoroughly ionized. Oxygen, which requires more energy to ionize to its doubly ionized state, appears more prominently near the center. Hydrogen glows more prominently at larger distances where the radiation is weaker. The eye-like appearance comes from this layered structure: a bright blue-green inner region, a surrounding ring of reddish hydrogen, and a central point of light. The approximate bilateral symmetry, combined with the curved forms, creates the impression of an iris and pupil. In infrared wavelengths, the helix looks somewhat different. The cometary knots become more prominent in certain infrared bands, as the dense dusty heads of the knots absorb ultraviolet radiation and re-emit it as infrared. The outer halo, which is very faint in visible light, becomes more clearly visible in the far infrared, revealing the full extent of the earlier mass loss episodes. In radio wavelengths, the helix has been mapped in molecules such as carbon monoxide and formaldehyde, complex molecules that survive in the dense, shielded interiors of the cometary knots, protected from the ionizing radiation of the central star. The detection of molecules within a planetary nebula is significant because it shows that not all the expelled material is fully ionized. Some regions are dense enough to retain molecular chemistry. In X-rays, the central white dwarf glows, and there may be some diffuse X-ray emission from the hot inner region of the nebula as well. All of these observations, taken together, build a picture that no single image can convey. The Helix Nebula is simultaneously a radio source, an infrared source, an optical nebula, an ultraviolet emitter, and an X-ray source. It is a multi-wavelength phenomenon, and the famous photographs represent one particular window, a beautiful and informative one, but still just one way of seeing. The gas that makes up the Helix Nebula was once the outer layers of a star. That means it carries with it the chemical history of the star that expelled it, the elements synthesized in the star's interior over the course of its life, as well as the original material from the gas cloud that formed the star in the first place. The dominant component of the nebula, as with most planetary nebulae and most stars, is hydrogen. Hydrogen is the most abundant element in the observable universe, and it makes up the majority of the material in the helix. The second most abundant element is helium. But the star did not simply return hydrogen and helium to the interstellar medium. Over the course of its life, nuclear fusion in its core processed some of that hydrogen into heavier elements. Helium nuclei were fused into carbon. In some conditions, carbon and helium combined to produce oxygen. Nitrogen was produced in the hydrogen-burning shells that surrounded the core during the star's advanced stages. The Helix Nebula's chemical composition reflects these processes. Emission lines from ionized carbon, nitrogen, oxygen, and sulfur are all detectable in its spectrum. These are elements of moderate atomic weight, what astronomers broadly call metals, a term used for all elements heavier than helium. The carbon-to-oxygen ratio in the Helix Nebula has been studied to constrain models of the nucleosynthesis, the nuclear burning, that occurred inside the progenitor star. Different evolutionary models predict different ratios, and comparing observations to models helps astronomers understand which processes dominated. One of the particularly interesting chemical aspects of the helix involves the cometary knots. Their dense interiors have been detected to contain molecules, not just atoms, but bonded molecular species like diatomic carbon and carbon monoxide, as well as more complex molecules. This is somewhat surprising because the environment within a planetary nebula is generally quite hostile to molecular chemistry. The ultraviolet radiation tends to break apart chemical bonds. The knots survive as molecular reservoirs because their high densities allow them to shield their interiors from the radiation field. The detection of polycyclic aromatic hydrocarbons, large, flat, ring-shaped carbon molecules, in the infrared emission of some planetary nebulae is also of scientific interest. These molecules are thought to form in the dense winds of carbon-rich AGB stars, and they are widespread in the interstellar medium. They contribute to the characteristic infrared emission features seen in many astrophysical environments. When the Helix Nebula eventually disperses into the surrounding interstellar medium, which will happen over tens of thousands of years, the elements it contains will mix with the broader reservoir of gas and dust in our galaxy. That material will eventually be incorporated into new molecular clouds, and those clouds will collapse under gravity to form new stars and, around some of those stars, new planets. This is one of the fundamental cycles of stellar material in galaxies. Stars form from the interstellar medium. They process some of that material through nuclear fusion. They return it, enriched in heavier elements, to the interstellar medium when they die. The next generation of stars forms from a gas cloud that is slightly more chemically complex than the one that formed the previous generation. The oxygen in the water on Earth's surface, the carbon in every organic molecule in every living cell, these elements were synthesized inside stars that lived and died before our sun was born. They were expelled in episodes like the one we are observing in the Helix Nebula, and they drifted through space for millions of years before becoming part of the molecular cloud that eventually collapsed to form our solar system. The Helix Nebula is one member of a much larger class of objects. Planetary nebulae are found throughout our galaxy. Estimates suggest there may be 10,000 to 50,000 of them in the Milky Way, though relatively few have been cataloged precisely because many are distant, faint, or hidden behind dust clouds. Beyond our galaxy, planetary nebulae have been detected in many nearby galaxies as well, where they serve as useful distance markers because their luminosities fall within a characteristic range. The shapes of planetary nebulae are remarkably diverse. Some are simple, nearly spherical bubbles. Others are elongated bipolar forms, shaped like pinched hourglasses. Some have multiple concentric rings. Others show jets, clumps, arcs, and filamentary structures with no obvious symmetry. The helix, with its roughly face-on toroidal form, represents one particular type within this diversity. The reason for the diversity in shapes is an active area of research. Stellar rotation, binary companions, magnetic fields, and the timing and geometry of successive mass loss episodes all likely play roles. A star with a close binary companion may produce a very different nebula than a solitary star, because the companion's gravity can shape the outflowing material into bipolar structures along the orbital axis. There is some evidence that a majority of non-spherical planetary nebulae may have binary central stars, though this is difficult to confirm observationally because the companions are often faint and close to the bright remnant. Some well-known examples of planetary nebulae beyond the helix include the Ring Nebula in Lyra, a compact, visually striking ring about 2,300 light-years away. The Dumbbell Nebula in Vulpecula is larger and brighter, shaped like a double-lobed form. The Cat's Eye Nebula in Draco shows remarkable concentric shells and jets, suggesting a complex evolutionary history. The Butterfly Nebula, also known as NGC 6302, is a dramatic bipolar nebula with extremely hot central star and a complex dusty torus. The Southern Ring Nebula, also known as NGC 3132, became newly famous when it was among the first objects imaged in detail by the James Webb Space Telescope in 2022. The Webb images revealed a binary central star system, a confirmation of theoretical expectations, and intricate filamentary structures in extraordinary resolution. Each of these nebulae represents a different star's final gift to the interstellar medium. A different history, a different mass, a different companion situation, a different orientation. The Helix Nebula sits in this family as the closest and therefore the most readily studied member. Its proximity allows astronomers to resolve features that are simply too small to see in more distant nebulae. The cometary knots, for instance, are a feature that appears in other planetary nebulae as well, but the helix's nearness allows individual knots to be studied in detail that is simply not achievable elsewhere. The study of planetary nebulae connects to many broader questions in astrophysics, about how stars shed mass, about how the interstellar medium is enriched over cosmic time, about the final states of stars, about the formation of white dwarfs, and about the population of evolved stars and galaxies. The helix, as the nearest well-studied example, plays a foundational role in all of these areas. Knowing the distance to the Helix Nebula is essential to knowing anything else about it. Without distance, we cannot determine actual physical sizes, only apparent angular sizes. We cannot determine actual luminosities, only apparent brightnesses. Distance is a fundamental piece of information, and obtaining it for objects outside the solar system requires methods that are indirect and often uncertain. For the Helix Nebula, distance estimates have evolved over the decades as measurement techniques improved. Early estimates, based on statistical arguments and comparisons to other nebulae, placed it at various distances ranging from around 400 to 700 light-years. More recent measurements have converged on values in the range of 650 to 700 light-years. One important technique used for nearby stars is trigonometric parallax, the apparent shift in a star's position as Earth moves from one side of its orbit to the other over the course of a year. For the central white dwarf of the Helix Nebula, parallax measurements have been made by instruments both from Earth and from the Hipparcos satellite, which surveyed stellar positions with high precision in the 1990s. The Gaia mission, launched in 2013, has provided even more precise parallax measurements for a very large number of stars, and the central white dwarf of the Helix falls within its catalog. Current Gaia-based estimates of the distance are among the most reliable available. The expansion of the nebula itself also provides a way to cross-check the distance. By measuring the angular rate at which the nebula is expanding over time, comparing images separated by years or decades, and comparing this to the velocity of expansion measured from spectroscopy, astronomers can derive an independent distance estimate. This method is called the expansion parallax method, and for the helix it gives results broadly consistent with the direct stellar parallax. Spectroscopy, the analysis of light broken into its component wavelengths, is a crucial tool throughout the study of the helix. The wavelengths at which the nebula emits tell astronomers what elements are present. The widths and shifts of those spectral lines tell them how fast and in what directions the gas is moving, through the Doppler effect, which shifts wavelengths depending on whether the source is moving toward or away from the observer. Maps of velocity within the helix, derived from spectroscopic observations of different emission lines, show the expansion pattern in 3 dimensions, or as close to 3 dimensions as can be inferred from a 2-dimensional projection on the sky. These velocity maps are essential for constructing models of the nebula's structure. One additional method used in studying the helix is photoionization modeling. Astronomers construct numerical models of the nebula, specifying the distribution and density of gas, the temperature and luminosity of the central star, and the relevant atomic physics, and then compute what the model predicts for the observed emission line spectrum. By comparing model predictions to observations and adjusting the parameters, they constrain the physical conditions in the nebula. This kind of modeling involves significant computational resources and careful atomic physics, but it produces quantitative estimates of temperatures, densities, elemental abundances, and ionization states throughout the nebula. All of these methods, parallax, expansion parallax, spectroscopy, photoionization modeling, work together to build our current understanding of the helix. No single observation provides all the answers, but the convergence of multiple approaches gives confidence in the overall picture. The era of the James Webb Space Telescope, which began science operations in 2022, has opened new possibilities for observing planetary nebulae and objects like the helix. Webb is designed primarily as an infrared telescope. Its instruments detect light from near-infrared through mid-infrared wavelengths. This makes it particularly sensitive to the cooler, dusty components of nebulae, to molecular emission, and to objects that are obscured in visible light by dust. The Helix Nebula had already been studied extensively in the infrared by earlier telescopes, including the Spitzer Space Telescope, which operated from 2003 to 2020. Spitzer revealed the extent of the cometary knots in infrared light and detected the infrared excess around the central white dwarf that may indicate a dust disk. With Webb's far greater sensitivity and angular resolution in the infrared, detailed studies of the helix's cometary knots, molecular emission, and central structure become possible at levels not previously achievable. Webb observations of planetary nebulae, including the Southern Ring Nebula, the NGC 3132 system, have demonstrated the instrument's ability to reveal fine structure, detect molecular features, and characterize binary central star systems with unprecedented precision. The molecular content of the helix's knots, the question of what chemical species exist in the dense interiors of these cometary structures, is one area where Webb's spectroscopic capabilities in the infrared are particularly relevant. Molecules such as carbon monoxide and hydrogen-2 emit at infrared wavelengths, and Webb can resolve individual bright knots well enough to study their spectra separately. The study of the possible dust disk around the helix's central white dwarf is another area of ongoing interest. If there is indeed a disk of dusty material, possibly the shattered remains of an earlier planetary system, then Webb's sensitivity to thermal emission from warm dust would be well suited to characterizing it. Beyond the helix specifically, the context established by the new Webb-era observations of planetary nebulae more broadly is reshaping understanding of how these structures form and how they evolve. The exquisite images of the Southern Ring Nebula showed not only the binary central star but also faint emission from molecular hydrogen in the outermost region, extending our picture of where molecular material survives in these environments. The telescope has also been applied to other classes of objects that share features with the helix, preplanetary nebulae, which are objects in the brief phase between the AGB stage and full planetary nebula illumination, and young planetary nebulae where the central star is still partly embedded in its circumstellar envelope. All of this new data, accumulating through the ongoing operations of Webb and other advanced facilities, will continue to refine and deepen the understanding of objects like the helix over the coming years and decades. The Helix Nebula is, in this sense, a living subject of science, an object about which there is always more to learn. It is worth pausing here to consider the scales involved. The light that left the Helix Nebula and is arriving at our instruments right now has been traveling for approximately 650 years. When that light began its journey, it was the middle of the 14th century on Earth. The Black Death was moving through Europe. In China, the Yuan dynasty was in its final decades. In the Americas, the great Aztec Empire was newly founded. The invention of the movable type printing press was still roughly a century away. All of that history has transpired during the time that light was crossing the void between the helix and us. At its current expansion rate of around 31 kilometers per second, the Helix Nebula grows by about 1 billion kilometers per year. That sounds significant, but it is barely a fraction of its current diameter measured in light years. The nebula is not changing in any way that would be perceptible on a human timescale. Even over decades of careful observation, the change in angular size is tiny, measurable, but tiny. The central white dwarf, cooling at a rate determined by its mass and composition, has a cooling timescale of many billions of years. In 10 billion years, it will be cooler, dimmer, but still present, still slowly radiating. The nebula itself, continuing to expand into the surrounding interstellar medium, will eventually thin to the point of invisibility. Estimates place this dispersal at roughly several tens of thousands of years from the present. After that, the material will be indistinguishable from the background interstellar medium, incorporated into the broader reservoir of gas and dust in our part of the Milky Way. In galactic terms, none of these timescales are particularly long. The Milky Way is roughly 13 billion years old. The Sun has been orbiting the galactic center for about 20 orbits over its lifetime. The 10 to 50,000 years of a planetary nebula's visible lifetime is less than a single orbit. And yet, within that brief window, the Helix Nebula produces the extraordinary glow that we observe, a testament to the physics of ionized gas and ultraviolet radiation, operating on the cast-off outer layers of a star that lived for hundreds of millions of years. It is easy, sometimes, to think of the cosmos as distant and static. The objects in astronomical photographs look frozen, permanent, ancient. But everything we observe is in motion. Everything is in some stage of a process. The Helix Nebula looks today as it does because we are watching it at a particular moment, roughly 10,000 years into a process that began with a dying star and will end with dispersal into the interstellar medium. We are catching it mid-breath. The Helix Nebula occupies a particular place in popular science imagery that most astronomical objects do not. The photograph, specifically the composite Hubble-era image showing the deeply layered structure with its blue-green center and reddish outer ring, became widely circulated online in the early 2000s, often attached to the label the Eye of God or the Eye of the Universe. In some versions of this internet circulation, the image was presented with captions suggesting religious or philosophical significance, and email chains and social media posts gave it a kind of reverential framing. This gave the Helix Nebula a cultural presence that few comparable objects have achieved. People who had never heard of planetary nebulae, who had no prior interest in astronomy, encountered this image and found it compelling. The eye-like appearance, the sense of scale, the colors, all contributed to an image that felt, to many viewers, significant in a way that went beyond the purely scientific. Astronomers tend to be somewhat cautious about this framing. The resemblance to an eye is a coincidence of geometry and our pattern recognition instincts, not an intentional form. The colors in the image are produced by emission lines, not by any aesthetic design. And yet the widespread public interest generated by the image has undeniably increased awareness of planetary nebulae and of astrophotography more broadly. The Helix Nebula has appeared in numerous popular science books, magazine articles, television documentaries, and educational materials. It is included in the catalogs of the most visually striking objects in the observable sky, appearing alongside the pillars of creation in the Eagle Nebula, the Crab Nebula, and the Andromeda Galaxy as objects that have achieved a degree of public recognition extending beyond the scientific community. The name NGC 7293, its formal designation in the New General Catalog, the catalog of deep sky objects compiled originally by John Dreyer in the late 19th century, is well known to amateur astronomers. The NGC was based on and extended from earlier catalogs by William Herschel and his son John Herschel, and it remains a fundamental reference in observational astronomy. For amateur astronomers with appropriate equipment, the Helix Nebula is a rewarding target. It requires dark skies, its light is spread over a large angular area, reducing its surface brightness. But under good conditions, wide-field binoculars or a rich-field telescope can show the soft, circular glow of the nebula clearly. More detailed observations with larger amateur telescopes and narrowband filters can reveal the ring structure and, in photographs, begin to show some of the internal structure. The object has a certain quality, quiet, large, close, that makes it feel, to observers, somewhat different from the sharp, point-like stars around it. It is extended. It has form. It has depth, not in the physical sense of three-dimensional perception, but in the sense of structure and detail that invites the eye to explore it. Among the objects we can observe in the sky, it occupies a unique position. Not the most luminous, not the most distant, not the most dramatic in any superlative sense, but in some ways the most intimate of the great nebulae, the closest example of a process that will eventually happen to our own star. The Helix Nebula's progenitor star belongs to a family of stars that end their lives in this gentle, expansive way. Stars of low to intermediate mass, broadly those between roughly half the Sun's mass and about 8 times the Sun's mass, all follow a broadly similar final evolutionary path. Red giant, asymptotic giant branch, mass loss, planetary nebula, white dwarf. The differences between them lie in the details of how massive they were, how long they lived, how much material they expelled, and what kind of chemistry dominated their stellar winds. Stars less massive than the Sun evolve very slowly. The smallest stars, red dwarfs like Proxima Centauri, have such low masses and such efficient hydrogen burning that they may remain on the main sequence for trillions of years, far longer than the current age of the universe. None of these stars have yet evolved to the end of their main sequence lives, so we have no observational examples of their final stages. Theory predicts that they will simply cool and fade without a dramatic planetary nebula phase. Stars a bit more massive than the Sun, in the range from about 1 to a few solar masses, are the ones most clearly associated with planetary nebulae. The Sun itself, in about 5 billion years, will swell into a red giant, then an AGB star, and ultimately shed its outer layers to produce a planetary nebula. Whether the Sun's nebula will be as well-structured and as visible as the Helix is uncertain. It depends on details of mass loss and ejection geometry. But the broad process is the same. The Helix Nebula's progenitor star belongs to a family of stars that end their lives in this gentle, expansive way. Stars of low to intermediate mass, broadly those between roughly half the Sun's mass and about 8 times the Sun's mass, all follow a broadly similar final evolutionary path. Red giant, asymptotic giant branch, mass loss, planetary nebula, white dwarf. The differences between them lie in the details of how massive they were, how long they lived, how much material they expelled, and what kind of chemistry dominated their stellar winds. Stars less massive than the Sun evolve very slowly. The smallest stars, red dwarfs like Proxima Centauri, have such low masses and such efficient hydrogen burning that they may remain on the main sequence for trillions of years, far longer than the current age of the universe. None of these stars have yet evolved to the end of their main sequence lives, so we have no observational examples of their final stages. Theory predicts that they will simply cool and fade without a dramatic planetary nebula phase. Stars a bit more massive than the Sun, in the range from about 1 to a few solar masses, are the ones most clearly associated with planetary nebulae. The Sun itself, in about 5 billion years, will swell into a red giant, then an AGB star, and ultimately shed its outer layers to produce a planetary nebula. Whether the Sun's nebula will be as well-structured and as visible as the Helix is uncertain. It depends on details of mass loss and ejection geometry. But the broad process is the same. Stars in the range of about 5 to 8 solar masses follow a somewhat more accelerated version of the same path. They spend less time on the main sequence, evolve more quickly through the red giant and AGB stages, and may produce more luminous and more chemically complex nebulae before leaving more massive white dwarfs. Stars above roughly 8 to 10 solar masses follow a completely different final path. Rather than shedding their outer layers gently, they build up an iron core that collapses under gravity, triggering a supernova explosion. These stars do not leave white dwarfs. They leave neutron stars or black holes. The material they return to the interstellar medium is enriched in heavier elements, the products of more extreme nuclear burning, and the energy of the explosion disperses material at much higher velocities. The Helix Nebula is an example of the gentle path, the one that does not end in a supernova, but in a slow, extended exhalation. Within the family of planetary nebulae, there are several nearby examples that can be compared to the Helix. The Ring Nebula in Lyra is smaller in angular extent but very well studied, and it has served as a kind of reference object for understanding the physics of ionized nebulae. The Dumbbell Nebula is brighter and more complex in shape. The planetary nebula NGC 246 is another relatively close example in the constellation Cetus. The Able Catalogue of Planetary Nebulae, compiled in the 1960s, includes many large, faint, and relatively nearby objects, most of them at more advanced stages of evolution than the Helix, and correspondingly more difficult to observe because they are both large in angular extent and very low in surface brightness. The Helix, by contrast, is bright enough and close enough that it bridges the world of serious amateur observation and professional scientific study. It is the kind of object that a skilled amateur can observe tonight with modest equipment, and that professional astronomers with space telescopes are still actively studying. Let us return more slowly now to the nebula itself. Somewhere in the southern sky, in the direction of Aquarius, there is a ring of glowing gas 2 light-years across. It is expanding. It has been expanding for 10,000 years. It will continue expanding for tens of thousands of years more. At its center, A small, dense star no larger than our planet is slowly cooling. It will cool for billions of years, long after every living thing we know of has completed its existence. That remnant will still be slowly releasing its stored heat into the void. The gas around it, the expelled layers of the star that once was, contains hydrogen, helium, oxygen, nitrogen, carbon. It glows in the specific wavelengths those atoms emit when they capture electrons. Blue-green oxygen near the center, red hydrogen farther out. The inner geometry of the nebula reflects the distribution of temperatures and densities across the 2 light-year span. And within the glowing ring, there are the knots. 20,000 of them, roughly the size of solar systems, with bright heads and long trailing tails all pointing outward like a field of frozen droplets blown by an invisible wind. Each one dense enough to shield its interior from the radiation that has ionized everything else around it. Each one, perhaps, carrying molecular chemistry within its protected core, carbon monoxide, possibly, and other species that could not exist in the harsher, more exposed regions of the nebula. These knots will not survive indefinitely. Over thousands of years, the radiation will slowly erode their surfaces. The heads will gradually thin, the shielded interiors will become exposed to the field, and eventually the molecules within will be broken apart and ionized. But right now, at this particular moment in the nebula's evolution, they persist. It is tempting to think of this as a dramatic process, the destruction of molecular reservoirs by a relentless radiation field. But on human timescales, none of it appears dramatic. The nebula looks the same tonight as it did a century ago. The knots are in essentially the same positions. The white dwarf is at the same temperature, to any observable precision. The expansion has increased the nebula's diameter by an amount far too small to measure without careful comparison of precise images. What changes over human timescales is our understanding, not the object itself. In the early 19th century, when Carl Harding first recorded this faint glow in Aquarius, he had no way of knowing what it was. The concept of a planetary nebula, as the expelled outer layers of a dying star, did not yet exist. The nature of stars, the processes of nuclear fusion, the existence of white dwarfs, none of this was known. What Harding recorded was simply a small, faint, extended patch of light, different from the point-like stars around it. Over the following 2 centuries, the understanding of that patch grew from a curious phenomenon to a classified type of object, to a subject of detailed physical analysis, to an object with a measured distance, a catalog spectrum, a mapped velocity field, a resolved population of cometary knots, a characterized central remnant, and now a target for the most advanced space telescopes in human history. The nebula did not change in that time. Our eyes changed. The Helix Nebula is destined to return its material to the interstellar medium. The interstellar medium, the gas and dust that exists between stars in a galaxy, is not empty. It is, by the standards of laboratory science, extremely tenuous. A volume of interstellar space might contain only a few hydrogen atoms per cubic centimeter, compared to the approximately 10 billion atoms per cubic centimeter in Earth's atmosphere. But over the vast volumes of galactic space, this tenuous material accumulates to an enormous mass. The interstellar medium is not uniform. It exists in several distinct phases, ranging from cold, dense molecular clouds where new stars form, to warm atomic gas, to hot, diffuse plasma heated by supernovae and stellar winds. These phases exist in rough pressure balance with one another, exchanging material as events like supernova explosions compress and heat the surrounding medium, and as radiative cooling allows hot gas to cool and condense. When the Helix Nebula expands to the point where its density drops to the level of the surrounding interstellar medium, a process that will take many thousands of years, the material will no longer be distinguishable as a discrete nebula. It will become part of the broader reservoir. That reservoir is used to form new stars. Dense regions of the interstellar medium molecular clouds are the birthplaces of stars. When a molecular cloud is compressed, perhaps by the shock wave from a nearby supernova, or by the passage through a spiral arm of the galaxy, or by gravitational instabilities within the cloud itself, it can begin to collapse. Denser cores within the cloud collapse more rapidly, heating up and eventually igniting nuclear fusion to become new stars. Each new generation of stars forms from a medium that has been enriched by the outputs of the previous generation. The oxygen, carbon, and nitrogen that the Helix Nebula will one day return to the interstellar medium will, billions of years from now, be incorporated into new stars and new planetary systems. This is one of the most profound cycles in nature, not rapid, not observable on human timescales, but operating continuously across the history of the galaxy. The Milky Way itself is approximately 10 to 13 billion years old. Over that time, many generations of stars have lived and died. The first stars, forming from primordial hydrogen and helium in the early universe, had no heavy elements. Their explosions and mass loss events were the first major source of enrichment. Subsequent generations formed from increasingly enriched material, and each generation produced still more heavy elements that were returned to the medium. Our Sun, forming about 4.6 billion years ago, formed from material that had already been through multiple stellar generations. The carbon in organic molecules, the oxygen in water, the silicon in rock, the iron in metal, these elements were produced inside stars that lived and died long before the solar system existed. The Helix Nebula is, in this sense, one chapter in a very long book, one episode in a cycle of stellar birth, nuclear processing, and dispersal that has been ongoing since the earliest stars formed in the young universe. The star that created the Helix Nebula belongs to a classification scheme that astronomers use to organize the properties of stars. Stars are classified primarily by their spectral types, categories defined by the absorption lines visible in their light, which in turn reflect their surface temperatures. The sequence runs from the hottest to the coolest: O, B, A, F, G, K, M, with various subtypes within each category. Our Sun is a G-type star, with a surface temperature of about 5,800 Kelvin. The progenitor of the Helix was likely a star of type A or F in its main sequence life, somewhat hotter and more massive than the Sun, but not dramatically so. In its AGB phase, the late evolutionary stage when it was shedding most of the material now forming the nebula, the star was probably classified as a Mira variable or a related type. Mira variables are large, cool, pulsating AGB stars that vary dramatically in brightness over periods of hundreds of days. They drive strong stellar winds that carry material away from the star at rates that can be substantial. After shedding most of its outer layers, the star transitioned through what is called a post-AGB phase, a brief period, lasting only thousands of years, during which the star contracts and heats up rapidly while the expelled material is still nearby. As the central remnant reached temperatures high enough to ionize the surrounding gas, the planetary nebula phase began. The white dwarf that remains is currently classified spectroscopically as a hot white dwarf with hydrogen and helium in its atmosphere. Over time, the atmospheric composition of white dwarfs evolves. The heavier elements settle out under the influence of gravity, while lighter hydrogen and helium float to the top. Some white dwarfs show only hydrogen. Others show only helium. The specific atmospheric composition tells a story about the star's history. White dwarfs are classified by their atmospheric composition using a letter code: DA for hydrogen atmosphere white dwarfs, DB for helium atmosphere, DO for hot white dwarfs with helium lines, and so on. The central star of the helix is classified as a DAO, meaning a hot white dwarf with hydrogen as the dominant atmospheric component but with detectable helium. The mass of the white dwarf has been estimated through spectroscopic analysis of its radius and surface gravity, two quantities that, combined with models of white dwarf structure, yield a mass. The mass is estimated at around 0.6 to 0.7 solar masses. This is somewhat typical for a white dwarf. Most known white dwarfs have masses in the range of 0.5 to 0.8 solar masses, with a peak in the distribution around 0.6. The relatively narrow range of white dwarf masses compared to the wide range of progenitor masses reflects the mass loss process. Most of the original star's mass is returned to the interstellar medium during the giant and AGB phases, and what remains is a remnant in a comparatively narrow mass range. The relationship between a white dwarf's mass and the mass of its progenitor is called the initial-final mass relation. This relation has been studied by observing white dwarfs in star clusters of known age, where the age tells astronomers how massive a star would just be reaching the end of its life, and comparing the cluster member white dwarf's masses to what would be expected from stars of that mass. The Helix Nebula, as one of the most well-characterized planetary nebula systems, contributes data points to these fundamental relations. The name helix comes from the Greek word for spiral or winding, the same root from which we derive words like helicopter and helix in biology, as in the double helix structure of DNA. The name was applied to this nebula because of the visual impression created by its ring structure, which in certain projections and with certain image processing can appear to have a slightly spiraling or wound quality. The name is somewhat loosely applied. The Helix Nebula is not a true spiral in any physically meaningful sense, but the name has persisted. The designation NGC 7293 comes from the New General Catalog, published by John Dreyer in 1888. The NGC was a massive compilation of deep sky objects, nebulae, star clusters, and galaxies, assembled from the observations of William Herschel, John Dreyer himself, and many others. The number 7,293 places it near the end of the catalog, which roughly corresponds to its being a later addition to the compiled observations. The alternative designation PK036-57.1 comes from the Perek-Cahutek catalog of planetary nebulae, published in 1967. This catalog assigns systematic designations based on galactic coordinates. The 036 refers to its galactic longitude and -57.1 to its galactic latitude, indicating it lies well below the plane of the Milky Way. The popular name Eye of God is entirely informal. It does not appear in any scientific catalog or paper. It emerged in popular culture, particularly via internet circulation of the famous Hubble composite photograph in the early 2000s. Some versions of this internet circulation attributed the image incorrectly or gave it fanciful captions. The scientific community generally uses the names Helix Nebula or NGC 7293, though Helix Nebula has become well established even in scientific contexts as a convenient informal designation. The star in its constellation, Aquarius, carries its own name history. Aquarius has been recognized as a constellation figure across multiple ancient cultures, including Babylonian, Egyptian, and Greek traditions. The stars within it carry mostly Arabic names from the medieval period, when Arabic astronomers preserved and extended the Greek astronomical tradition. The nearest bright star to the helix in the sky is known by its catalog designations rather than a traditional name, as it is relatively faint. Names accumulate around astronomical objects the way sediment accumulates around submerged objects. Layers from different periods, different traditions, different languages. The Helix Nebula carries in its naming a compressed history of European scientific tradition, Greek word roots, medieval Arabic astronomy, 19th century catalog making, and 21st century popular internet culture. For those who have access to a dark sky and binoculars or a small telescope, the Helix Nebula is an achievable observation. It is not an easy target, and it is not dramatic in the way that some deep sky objects are. But it is the kind of observation that, once made, carries a particular quality. The quiet satisfaction of knowing that the faint smudge visible through the eyepiece is an object of the type and scale described here. The best time to observe the helix from the northern hemisphere is from late summer into autumn, roughly September and October, when Aquarius is well placed in the evening sky. From southern hemisphere locations, it can be observed over a longer part of the year, and it rises higher in the sky, making the conditions somewhat more favorable. The first challenge in observing the helix is finding it. It lies in a region of Aquarius that is not immediately adjacent to any particularly bright stars. A finder chart is helpful, either a printed star atlas or a digital planetarium application. The nearby star Fomalhaut, the brightest star in the neighboring constellation Piscis Austrinus and one of the brightest stars in the entire southern sky, serves as a useful anchor point for navigating to the helix region. The second challenge is sky conditions. The Helix Nebula has a relatively low surface brightness. Its light is spread over a large area. Light pollution dramatically reduces the contrast between the nebula and the sky background, making it invisible from urban or suburban environments. A site well away from artificial light with the nebula well above the horizon offers the best conditions. With wide-field 10 by 50 binoculars under dark skies, the helix appears as a faint, slightly fuzzy circular glow, similar in size to a large star cluster, but with a soft, diffuse quality rather than being resolvable into individual stars. The overall impression is of a large, pale circle, somewhat brighter at the edges than at the center in some observations. With a small telescope, say 150 mm aperture, under dark skies, the ring structure becomes somewhat more apparent. Adding a narrowband filter, particularly one transmitting the oxygen-3 emission line, can dramatically improve the contrast of the nebula against the sky background, as the filter passes the bright nebular emission while suppressing the broad-spectrum sky glow. Observers who have used such filters often describe the improvement as transformative. Photographing the Helix Nebula with a camera and tracking mount yields results that improve with exposure time and image processing. Many amateur astrophotographers have produced beautiful images of the helix from their own backyards, revealing the ring structure, hints of the inner region's different color, and sometimes even suggestions of the cometary knot structure in longer exposures. There is a quality to observing or photographing an object like this, connecting one's own instruments to a stream of light that has been traveling for 650 years, that is quiet and somewhat remarkable. No special equipment is required to participate in it, beyond access to a dark sky and modest optics. The Helix Nebula rewards patience, as many astronomical objects do. The light arriving right now from the Helix Nebula left its source during the middle of the 14th century. At that moment, the nebula was expanding. The white dwarf at its center was cooling, slightly cooler than it had been the century before, slightly warmer than it would be the century after. The cometary knots were in slightly different positions than they are now, the trailing tails slightly shorter or longer, the erosion proceeding at its quiet rate. None of this was visible to anyone anywhere on Earth in 1374. Now, several hundred years of scientific development later, we point our instruments in that direction and the photons arrive, and we measure them, and we understand a great deal about where they came from and what they passed through on their way here. There is something worth pausing over in that. Not a dramatic something, but a quiet one. The fact that light travels at a fixed speed means that looking at distant objects is always, in a precise sense, looking into the past. The further away something is, the older the light is when it arrives. The Helix Nebula as we observe it tonight is the Helix Nebula of several hundred years ago. If we could observe it as it is right now, this exact moment, we would need to wait another 650 years for that light to arrive. This is true of every star we can see. The stars in the night sky are not showing us the present. They are showing us history, an archive of different depths, depending on how far away each star is. The nearest stars are showing us a few years into the past. The stars of the Milky Way show us hundreds or thousands of years back. The distant galaxies visible in long-exposure photographs represent millions or billions of years of look-back time. The universe we observe is a layered archive. The Helix Nebula sits in the near part of that archive, the 650-year section, which by cosmic standards is essentially the recent past. The white dwarf at its center is the nearest remnant of a stellar death that we can study in detail. The material drifting through the nebula is the nearest example we have of matter being returned to the interstellar medium from a dead star. As you rest now or begin to drift, let these thoughts be quiet companions rather than active puzzles. 2 light years of glowing gas, slowly expanding. A star smaller than Earth at its center, slowly cooling. 20,000 cometary knots, each the size of a solar system, trailing outward through the glowing ring. A photograph that looks like an eye because our brains, wired for faces and forms, see an eye in the coincidental geometry of physics. And the light itself, the photons that carry all this information, traveling through space at 300,000 kilometers per second for 650 years, crossing the galaxy's quieter outer regions, passing through the sparse interstellar medium of our galactic neighborhood, eventually entering our solar system, reaching our telescopes, striking our detectors. A journey that began centuries ago, ending in a measurement. There is no urgency to any of this. The nebula will continue to expand whether or not we observe it. The white dwarf will continue to cool. The material will eventually disperse and become something else. The raw ingredient of a new cloud, of a new star, far in the future, in a part of the galaxy we cannot predict. The universe continues its patient processes regardless of what any observer makes of them. What we contribute when we look is simply attention. The quiet, unhurried kind. The kind that sees a faint circular glow in the constellation Aquarius and understands, however partially, however incompletely, what it is and where it comes from. That seems like enough. The Helix Nebula drifts slowly through the night. The light continues to arrive. The instruments continue to record it. And somewhere, someone is listening to this and letting their eyes close a little further. There is nothing you need to know right now. There is nowhere you need to be. The nebula has been there for 10,000 years and will be there, in some form, for many thousands more. This moment and this quiet are enough. Good night. To understand what the Helix Nebula is and why it glows, it helps to spend some time with the physics of ionization. An atom, in its neutral state, consists of a nucleus, protons and neutrons bound together, surrounded by electrons arranged in shells according to the laws of quantum mechanics. Different elements have different numbers of protons, and those protons define the element. Hydrogen has 1 proton, helium has 2, oxygen has 8, carbon has 6, nitrogen has 7. Each element in its neutral state has the same number of electrons as protons. When a photon of light, a packet of electromagnetic energy, strikes an atom, it can transfer its energy to one of the electrons. If the photon carries enough energy, the electron can escape the atom entirely. This is ionization. The atom, having lost an electron, is now positively charged. It is an ion. The electron, now free, travels away from the atom until it encounters another ion and is recaptured. When an electron is recaptured by an ion, the process releases energy, not all at once, but in a cascade. The electron falls from higher energy states to lower ones, and at each step it emits a photon of a very specific wavelength. These emitted photons are the light we observe in emission nebulae. Each element and each ionization state of each element has its own characteristic set of emission wavelengths, a spectral fingerprint that is as unique as anything in nature. Hydrogen emits at specific wavelengths known as the Balmer series invisible light, with hydrogen alpha at 656 nanometers being the most prominent. Doubly ionized oxygen emits at around 496 and 501 nanometers. Singly ionized nitrogen emits near 654 and 658 nanometers. In the Helix Nebula, the ultraviolet radiation from the central white dwarf ionizes the surrounding gas across a large volume. The intensity of ionization decreases with distance from the central star as the radiation field weakens. Near the center, where the radiation is strongest, elements that require high energies to ionize, like doubly ionized oxygen, are prominently ionized. Further out, where the radiation is weaker, only elements that ionize more easily remain ionized, and ultimately the material transitions to a neutral or molecular phase. This gradient of ionization is visible in the images of the Helix Nebula as the change in color from the blue-green inner region to the red outer ring. The colors in the image are not arbitrary. They map directly to the physical conditions in the gas. The process of ionization and recombination is continuous. Photons from the white dwarf are constantly ionizing atoms. Those ionized atoms are constantly recapturing electrons and emitting light. The nebula is not a static object glowing from stored energy. It is a dynamic system, constantly processing radiation from its central source and re-emitting it at lower energies. The total luminosity of the Helix Nebula, the total power it radiates, is closely related to the luminosity of the central white dwarf in ultraviolet wavelengths. Much of the energy emitted by the white dwarf is absorbed by the surrounding gas and re-emitted as visible light. The nebula is, in a sense, an energy converter, transforming high-energy ultraviolet photons into lower-energy optical photons that we can observe more easily. The specific intensities of different emission lines provide astronomers with diagnostic information. The ratio of certain oxygen lines to hydrogen lines is sensitive to the electron temperature in the gas, the average kinetic energy of the free electrons. By measuring these ratios carefully and comparing to theoretical models, astronomers can determine that the electron temperature in the Helix Nebula's emitting regions is roughly 8,000 to 12,000 Kelvin. This is far hotter than the surface of the Sun, but cooler than the central white dwarf. It reflects the temperature to which the gas is heated by the ionization process. Similarly, the density of the gas can be estimated from the ratio of certain line pairs that are sensitive to density. In the main emitting regions of the helix, the electron density is estimated at roughly a few hundred to a few thousand electrons per cubic centimeter sparse by laboratory standards, but enough to produce the glow we observe over the large volumes involved. All of this analysis comes from spectroscopy, the patient analysis of light broken into its component wavelengths. It is one of the most powerful tools astronomers have, and the Helix Nebula is one of the objects where it has been applied most extensively. The Sun is now approximately 4.6 billion years old. It is roughly halfway through its main sequence life, the long, stable phase of hydrogen fusion. In approximately 5 billion years, the hydrogen in the Sun's core will be exhausted. What happens then is worth understanding both for its own sake and for what it tells us about objects like the Helix Nebula. When the core runs out of hydrogen to fuse, the energy generation in the core stops. Without the outward pressure from fusion, gravity causes the core to contract. As the core contracts, it heats up. This heat is conducted to the surrounding shell of hydrogen just outside the depleted core, causing that shell to begin fusing hydrogen more vigorously than before. The increased energy output from the shell source pushes the outer layers of the Sun outward. The Sun expands. Over millions of years, it grows larger and cooler at its surface, becoming redder in color, becoming a red giant. At its largest, the Sun is expected to expand to roughly 1 to 2 astronomical units in radius, engulfing or coming very close to engulfing the inner planets, including Earth. During this expansion, the Sun's outer atmosphere becomes very loosely bound. Stellar winds increase in strength. The Sun begins to shed mass at an increasing rate, returning material to the interstellar medium. The Sun then enters the asymptotic giant branch phase, the AGB, characterized by alternating hydrogen and helium shell burning, strong pulsations, and significant mass loss through a dusty stellar wind. Over this phase, the Sun will shed a large fraction of its current mass, perhaps half or more, into the surrounding space. This material forms a circumstellar envelope. Eventually, the remnant core, the future white dwarf, is exposed. As it heats up, its ultraviolet radiation ionizes the surrounding expelled gas, and a planetary nebula forms. The planetary nebula of our Sun will be visible from elsewhere in the galaxy. What it will look like depends on the details of the mass loss process, which are not precisely predictable. But it will likely be a ring or bubble of glowing gas, a few light years across, fading over tens of thousands of years. From Earth's perspective, if Earth survives the Sun's red giant phase, which is uncertain, the inner solar system would by then be either engulfed or severely altered. Nothing of the current biosphere or of human civilization, if it still exists in any form, would remain. This is not a concerning thought so much as a factual one. It is simply the natural lifespan of a star and its associated planetary system. The white dwarf left by our Sun will be small, dense, and very hot. It will cool over billions of years. Eventually, after tens of billions of years of cooling, it will become a dim, cool object, a faded remnant of what was once the center of our solar system. What the Helix Nebula shows us is that this process is real. It is not theoretical. It has happened to the star at the center of the helix, and we can see the result. The white dwarf is there. The nebula is there. The cometary knots are there. The chemistry is there. Our Sun's future is already written. In some sense, in the light arriving from the direction of Aquarius every clear night. The shaping of the Helix Nebula's structure is not driven by radiation alone. Stars like the one that created the helix have magnetic fields. The magnetic field of the Sun, for comparison, is complex, a global dipole modified by differential rotation and convection, emerging at the surface in the form of sunspots, active regions, and the global heliospheric magnetic field that extends throughout the solar system. In AGB stars, the highly evolved, pulsating giants that are the direct progenitors of planetary nebulae, the magnetic field is uncertain. These stars have deep convective zones that can amplify and disorder the magnetic field. The interaction between a pulsating, convective atmosphere and a magnetic field is difficult to model. Direct measurements of magnetic fields in AGB stars are challenging because of the complexity of their spectra. Nevertheless, there is reason to believe that magnetic fields play a role in directing the stellar winds of AGB stars, helping to collimate material along certain directions rather than allowing it to spread perfectly symmetrically. This could contribute to the non-spherical shapes of many planetary nebulae, including any departure from perfect symmetry in the helix. The stellar wind itself, the outflow of particles and gas from the star, is a key driver of the mass loss process. In AGB stars, the wind is driven by a combination of radiation pressure on dust grains and the pulsations of the star. Dust grains, once they form in the cooler outer atmosphere, are efficiently pushed outward by radiation pressure. As they move out, they drag the surrounding gas with them, carrying mass away from the star. The rate of mass loss in AGB stars varies with the evolutionary stage. In the most extreme episodes, called superwind phases, the mass loss rate can reach values that strip the outer layers of the star very rapidly in geological terms. These superwind events are what ultimately reveal the white dwarf core. After the planetary nebula forms, the white dwarf itself continues to drive a wind of its own. A hot, fast, tenuous wind very different from the slow, dense AGB wind. This fast wind, traveling at hundreds or thousands of kilometers per second, overtakes and shocks the slower AGB wind material. The boundary between the fast and slow winds, the interface where they collide, can create the shell-like structures visible in the inner regions of some planetary nebulae. In the helix, evidence for a hot inner wind is found in X-ray observations and in the detailed structure of the inner ring. The interaction between winds of different epochs and different velocities is part of what produces the layered, complex appearance of the nebula. The cometary knots, discussed earlier, form in the regions where these winds interact, where the faster post-AGB outflow encounters the denser material expelled earlier. Their alignment, all pointing outward from the central remnant, is a direct geometric signature of this interaction. Wind interaction, radiation pressure, magnetic fields, rotation of the progenitor star, the gravitational influence of any companion bodies, all of these contribute to the final form of a planetary nebula. In the helix, the combination of these factors has produced the structure we observe: a slightly inclined torus, inner disk, outer halo, and 20,000 cometary knots. One of the interesting questions in the study of planetary nebulae is the role that binary star systems may play in shaping them. A binary star system is one in which two stars orbit each other, a very common configuration. It is estimated that roughly half of all Sun-like stars exist in binary or multiple star systems. The separation between the two components varies enormously, from pairs that orbit each other in hours, nearly touching, to pairs separated by thousands of astronomical units, barely interacting at all. When one star in a binary system evolves to become an AGB star and begins to lose mass, the presence of a companion can have a significant effect. If the companion is close enough, the slow AGB wind may be gravitationally focused by the companion, creating an asymmetric outflow. Material may accumulate in a disk around the companion or around the center of mass of the system. In some cases, the companion may be engulfed by the expanding giant, leading to a common envelope phase where both stars orbit within a shared envelope of gas. Common envelope evolution is a particularly dramatic scenario. Inside the common envelope, the orbital separation of the two stars decreases rapidly due to friction with the surrounding gas. The gravitational energy released as the orbit shrinks goes into ejecting the envelope. The result is a close binary system containing a white dwarf and a companion star, surrounded by the expelled common envelope, which becomes the planetary nebula. This process is thought to be responsible for many of the highly non-spherical bipolar planetary nebulae, the hourglass shapes, the highly elongated forms, the objects with strong jets. When the binary orbit is nearly circular and the outflow is concentrated along the orbital axis, the result is a bipolar nebula. Two lobes of gas on opposite sides, separated by a dense equatorial torus. For the Helix Nebula, the evidence for a binary central star is less clear than for some other planetary nebulae. The nebula structure is broadly consistent with a single-star origin, though the slight misalignment between the inner disk and the outer ring has been used to argue for some form of binary influence in the past. Dedicated searches for variability in the central white dwarf, which would indicate a close orbiting companion, have not conclusively identified one. However, the absence of a confirmed companion does not rule out the influence of a more distant companion, or a companion that was engulfed and is no longer separately detectable. The relationship between binary star evolution and planetary nebula shaping is an active area of research, with the James Webb Space Telescope and other modern facilities providing new evidence. The detailed study of the Southern Ring Nebula by Webb, showing the binary central star clearly, has reinvigorated interest in this topic across the planetary nebula community. For the Helix, the question remains open. Its structure can be explained by single-star models, but the complexity of the inner morphology, the multiple rings with different orientations, leaves room for the possibility of a more complex history. The Helix Nebula, at 650 light-years, is a neighbor of our Sun in the broader context of the Milky Way. The Milky Way is a barred spiral galaxy, a vast collection of several hundred billion stars arranged in a flattened disk with spiral arms extending outward from a central bar-shaped structure. The disk is roughly 100,000 light-years across and a few thousand light-years thick. The Sun sits roughly 26,000 light-years from the galactic center, in a relatively quiet part of the disk between two major spiral arms. At 650 light-years, the Helix Nebula is essentially in the same galactic neighborhood as the Sun. The distance to the galactic center is about 40 times the distance to the helix. In the context of a galaxy spanning 100,000 light-years, the Sun and the helix are practically adjacent. The local neighborhood of the Sun, the region within a few thousand light-years, is characterized by several large interstellar gas and dust structures collectively called the local bubble. This is a region of relatively hot, low-density plasma, thought to have been created by a series of supernova explosions several million years ago. The Sun sits near the interior of this bubble, which extends for hundreds of light-years in most directions. The Helix Nebula also sits within or near the local bubble. The low-density environment of the bubble means that the helix is expanding into relatively sparse surrounding material, which may influence the shape and visibility of its outermost regions. The direction of the helix from the Sun, toward the constellation Aquarius, corresponds to a direction that points somewhat downward from the plane of the Milky Way, toward the southern galactic hemisphere. The galactic latitude of the helix is about -57 degrees, meaning it sits well below the disk of the galaxy. This is why the region of sky around Aquarius appears sparse in stars. We are looking out through the thin part of the galactic disk and into the halo, rather than along the densely populated disk plane. The relatively low stellar density in the direction of the helix also contributes to its visibility. There is less interstellar dust along the line of sight than would be the case for an object closer to the galactic plane, so the nebula's light reaches us with relatively little absorption or scattering. In the broader structure of the Milky Way, the Helix Nebula is a fleeting structure. Even at its current age of 10,000 years, it has existed for only a tiny fraction of the Milky Way's multi-billion-year history. The white dwarf at its center will persist for billions of years, but the visible nebula will fade to invisibility within the next few tens of thousands of years. Stars, star clusters, interstellar clouds, all the features of the galaxy are dynamic, though the timescales are long enough that on human scales they appear static. The Milky Way we see tonight is a snapshot of a continuously evolving system. The Helix Nebula is one small, brief, beautiful feature in that ongoing evolution. The Helix Nebula has been the subject of study by a remarkable range of observatories, each contributing observations in different wavelength ranges and with different capabilities. On the ground, the helix has been observed by some of the world's most capable radio telescopes, instruments that detect electromagnetic radiation at centimeter and millimeter wavelengths. Radio observations of the helix have mapped emission from atomic hydrogen, from molecular carbon monoxide, from formaldehyde, and from other species. These observations require large dish antennae or arrays of smaller dishes working together. The Very Large Array in New Mexico, a famous array of 27 movable radio dishes that together form a powerful interferometer, has been used to study the radio emission from the helix and other planetary nebulae. The Australian Telescope Compact Array, operated by CSIRO in Australia, is particularly well-placed to observe the helix given its southern sky position. In the infrared, the Spitzer Space Telescope provided detailed images and spectroscopy of the helix across its operational lifetime from 2003 to 2020. Spitzer's 4 instruments, 2 cameras and 2 spectrographs covering wavelengths from roughly 3 to 160 micrometers, allowed comprehensive mapping of the dust emission, molecular emission, and the thermal structure of the cometary knots. The WISE mission, the Wide Field Infrared Survey Explorer, produced all-sky infrared images at several wavelengths, and the helix is visible in the WISE data as a prominent extended object in the mid-infrared. In the near-ultraviolet and visible, the Hubble Space Telescope has produced some of the most iconic and scientifically useful images of the helix. Hubble's advanced camera for surveys and wide-field planetary camera have been used to image the cometary knots in detail and to map the emission structure of the inner ring. The Galaxy Evolution Explorer GALEX, a space telescope designed to observe in the ultraviolet, observed the central white dwarf and the nebula in far and near ultraviolet, characterizing the hot radiation field from the remnant. The XMM Newton and Chandra X-ray observatories have both observed the Helix's central white dwarf and searched for diffuse X-ray emission from the hot inner nebula. Ground-based wide-field telescopes, particularly those equipped with large-format CCD detectors and narrowband emission line filters, have produced images of the helix that capture its full extent, including the faint outer halo. Instruments at Kitt Peak National Observatory, the European Southern Observatory, and other major ground facilities have contributed to this work. Each facility has added to the picture in its own way. No single observatory can observe across all relevant wavelengths, and the multi-facility character of the Helix Nebula study is not unusual in modern astronomy. It reflects the fundamental reality that different physical processes emit in different parts of the spectrum, and understanding any complex astrophysical object requires a multi-wavelength approach. The Helix Nebula does not sit alone in its part of the sky. The constellation Aquarius and its surroundings contain several other objects of interest, though none as striking as the helix itself in terms of scientific importance. Aquarius is a large constellation. It extends across a substantial area of the sky and contains a number of notable stars. The brightest star in Aquarius, Sedalsud, is a yellow supergiant star approximately 610 light-years away. Its name comes from Arabic meaning the luckiest of the lucky, a designation that reflects its rising with the sun at the time of the spring equinox in ancient times, signaling the return of warm weather in the region where the Arabic astronomical tradition was developed. Nearby is Sadelmelik, another yellow supergiant with a similarly auspicious Arabic name meaning the lucky stars of the king. Both stars are considerably larger than the sun and approaching the end of their main sequence or supergiant phases. The constellation also contains another famous deep sky object, the Saturn Nebula, designated NGC 7009. This is another planetary nebula, smaller and more compact than the Helix, with ANSI, handle-like extensions on either side of its main elliptical disk, that give it a superficial resemblance to the planet Saturn with its rings, hence the name. The Saturn Nebula is much more distant than the Helix, roughly 2,000 to 4,000 light-years away, and its angular diameter is much smaller, making it look like a small oval disk through a telescope. The Helix Nebula sits not far on the sky from the bright star Fomalhaut in the neighboring constellation Piscis Austrinus. Fomalhaut is interesting in its own right. It is one of the nearest bright stars to the Sun, only about 25 light-years away, and it is surrounded by a prominent dusty debris disk observed in detail by Hubble and Herschel. Fomalhaut's disk is thought to be analogous to the Kuiper belt in our solar system, a ring of icy debris left over from planetary formation. Several claimed planetary candidates have been associated with this disk, though the evidence has been debated. The region of sky around Aquarius, being far from the plane of the Milky Way, is a window through which we see many distant galaxies. Deep imaging of fields in this area reveals background galaxies at enormous distances, millions and billions of light-years away, their light having traveled through most of the universe's history to reach our detectors. In this one field of sky, this one direction we call Aquarius, there are thus objects at many distances, representing many different stages of cosmic history. The nearby white dwarf and its nebula at 650 light-years, the supergiants Sedalsud and Sadelmelik at similar distances, Fomalhaut at 25 light-years, and beyond all of these, the distant galaxies at cosmological distances. The sky is not a flat backdrop. It is a depth. Light is what connects us to the Helix Nebula. It is, in fact, the only way we know anything about it. Light, electromagnetic radiation, travels through the vacuum of space at approximately 299,792 kilometers per second. This is the cosmic speed limit, as described by Einstein's theory of special relativity, and it applies to all electromagnetic radiation regardless of wavelength or frequency. Light has a dual nature. It can be described as a wave, oscillating electric and magnetic fields propagating through space, or as a stream of particles called photons. In quantum mechanics, both descriptions are correct in different contexts. The wave description is most useful when understanding diffraction and interference. The particle description is most useful when understanding absorption and emission. When a photon is emitted by an excited atom in the Helix Nebula, say an oxygen atom recapturing an electron, it carries a specific amount of energy determined by the energy difference between the quantum states involved. That energy is fixed. travels through space at the speed of light, unmodified, until it interacts with something. Over its journey from the helix to Earth, the photon passes through a nearly perfect vacuum. The interstellar medium, while not empty, is so tenuous that photons can travel hundreds of light-years through it with very little chance of interaction. The photons from the helix arrive at our detectors much as they left, with the same energy, the same direction of travel, the same information about the atom that emitted them. Our detectors, the sensors in astronomical cameras, work by absorbing photons and converting their energy into electrical signals. A silicon-based detector, such as a charge-coupled device, absorbs a photon and uses its energy to free an electron within the silicon lattice. This electron contributes to a measured current, and by counting these events, astronomers can build up an image of the sky. The efficiency of this process, what fraction of incoming photons are actually detected, has improved enormously over the decades of astronomical instrumentation. Modern CCDs and their successors can detect 80% or more of the photons that reach them across a wide range of wavelengths. This represents a dramatic improvement over the photographic plates used in earlier astronomy, which detected only a few percent of incident photons. The information content in light is extraordinary. The energy of a photon tells us the wavelength, which tells us the emission process. The direction from which it comes tells us where the source is. Tiny Doppler shifts in wavelength tell us how fast the source is moving along the line of sight. Polarization of the light tells us about magnetic fields and scattering geometries. Variability in brightness over time tells us about physical changes in the source. From a stream of photons, arriving at a detector at the rate of perhaps a few per second from a faint nebula, astronomers can extract an extraordinary amount of physical information. It requires careful instrument design, careful calibration, careful analysis, but the information is there, encoded in the light. The tools available for studying objects like the Helix Nebula will continue to develop in the coming decades. The James Webb Space Telescope, now operational and returning extraordinary data, will continue to study planetary nebulae and the progenitor AGB stars, improving our understanding of the mass loss processes and the chemical enrichment they produce. Webb's sensitivity and resolution in the infrared exceed anything previously available, and the science it enables is still unfolding. Ground-based astronomy is also advancing. The next generation of extremely large telescopes, instruments with mirror diameters of 30 meters and more, are under construction. The extremely large telescope being built in the Atacama Desert of Chile by the European Southern Observatory, the 30-meter telescope, and the Giant Magellan Telescope will all offer angular resolution and light-collecting area far beyond current ground-based capabilities. These instruments will be able to resolve fine details in nearby planetary nebulae, including the helix, at levels not yet achieved. Individual cometary knots, currently resolved in Hubble images, will be observed with even finer detail by the ELT, allowing studies of their internal structure, velocity fields, and chemistry that are not currently possible. Radio astronomy is also advancing. The square-kilometer array, currently under construction in South Africa and Australia, will provide centimeter and meter wavelength observations of extraordinary sensitivity. The SKA will be able to detect very faint radio emission from planetary nebulae, map their magnetic fields through Faraday rotation, and characterize their molecular content in ways not currently achievable. Space-based ultraviolet astronomy, one of the wavelength ranges where the central white dwarfs of planetary nebulae emit prominently, has been somewhat underserved since the Galaxy Evolution Explorer concluded its operations. Future ultraviolet space missions would greatly benefit studies of hot white dwarfs and the ionization fields they produce. All of these advances will continue to refine and deepen the picture of objects like the Helix Nebula. New observations will answer current questions and certainly generate new questions in turn. This is the nature of science. Each generation of instruments and observations advances understanding while also revealing new puzzles. The Helix Nebula, studied continuously since the 19th century, will continue to be a subject of new observations and new analysis for as long as the relevant facilities exist and astronomers choose to point them in that direction. There is something quietly satisfying in that. An object that has been slowly expanding through space for 10,000 years, observed by human instruments for 200 years, will continue to be studied with ever-improving tools for as long as scientific civilization persists. The nebula does not know it is being observed. It simply continues its patient process. But the observation continues, and through it, understanding deepens. We have traveled a long way tonight. Not in any physical sense, of course. You have been wherever you are, in bed, perhaps, or resting somewhere quiet. But in terms of the ground we have covered in thought and in information, we have traversed quite a distance. We began with a soft introduction, a quiet invitation to set aside the urgency of the day and give some attention to a single object in the southern sky. An object known by several names. The Helix Nebula. NGC 7293. The Eye of God. We looked at what it is. A planetary nebula. The expelled outer layers of a dying star, glowing in the ionizing radiation of the white dwarf remnant at its center. We found its location, in the constellation Aquarius, about 650 light-years away, making it the nearest well-studied planetary nebula to Earth. We examined its structure, the outer reddish ring of hydrogen, the inner blue-green region of ionized oxygen, the roughly 20,000 cometary knots with their vast tails all pointing outward from the center, the multiple rings oriented at slightly different angles, the faint outer halo. We followed the life of the star that made it, from a main sequence star probably 2 to 4 times the mass of our Sun, through the red giant phase, through the asymptotic giant branch with its strong winds and pulsations, to the shedding of the outer layers and the exposure of the white dwarf core. We spent time with the white dwarf itself. Small, dense, extremely hot, slowly cooling over billions of years, still radiating intensely in ultraviolet wavelengths and driving the glow of the surrounding gas. We looked at the light from the nebula, how it carries information about temperature, density, chemical composition, and motion. How spectroscopy can extract that information. How images assembled from multiple wavelengths reveal the physical structure that no single window of observation can show fully. We considered the chemistry, the hydrogen and helium dominant throughout, the enriched oxygen, nitrogen, and carbon that the star synthesized in its interior and returned to the interstellar medium. The molecules persisting in the protected interiors of the cometary knots. The polycyclic aromatic hydrocarbons and carbon chain molecules of the stellar wind. We placed the nebula in context, within the family of planetary nebulae, within the Milky Way, within the cosmic cycle of stellar birth and death and enrichment and renewal. We considered what it means for our own solar system's future, the Sun following the same general path in about 5 billion years, eventually producing its own planetary nebula, leaving its own white dwarf to cool alone in space. And we have come, now, to the end of what there is to say tonight. The Helix Nebula will be there tomorrow night, and the night after that. It will be there for tens of thousands of years, slowly expanding, slowly fading, until the material disperses and the white dwarf cools below visibility. Long after that, the white dwarf will still be present, a cold, dark remnant, orbiting the Milky Way for billions of years into the future, carrying the memory, in its composition, of the star it once was. There is nothing dramatic to conclude with, nothing that needs resolution or summary. The process simply continues, as it has been continuing for 10,000 years. We considered the chemistry, the hydrogen and helium dominant throughout, the enriched oxygen, nitrogen, and carbon that the star synthesized in its interior and returned to the interstellar medium. The molecules persisting in the protected interiors of the cometary knots. The polycyclic aromatic hydrocarbons and carbon chain molecules of the stellar wind. We placed the nebula in context, within the family of planetary nebulae, within the Milky Way, within the cosmic cycle of stellar birth and death and enrichment and renewal. We considered what it means for our own solar system's future, the Sun following the same general path in about 5 billion years, eventually producing its own planetary nebula, leaving its own white dwarf to cool alone in space. And we have come, now, to the end of what there is to say tonight. The Helix Nebula will be there tomorrow night, and the night after that. It will be there for tens of thousands of years, slowly expanding, slowly fading, until the material disperses and the white dwarf cools below visibility. Long after that, the white dwarf will still be present, a cold, dark remnant, orbiting the Milky Way for billions of years into the future, carrying the memory, in its composition, of the star it once was. There is nothing dramatic to conclude with, nothing that needs resolution or summary. The process simply continues, as it has been continuing for 10,000 years. A ring of glowing gas, 2 light-years across, in the southern constellation of Aquarius. A white dwarf at its center, smaller than Earth, carrying the mass of more than half the Sun. 20,000 cometary knots, each the size of a solar system, trailing their dusty tails outward through the glowing ring. And the light, always the light, traveling outward in all directions from the nebula, some of it aimed at Earth, some of it arriving at our instruments this very night. If you are still awake, let these images settle quietly into wherever they fit in your mind. If you have already drifted off, that is exactly as it should be. The information was here, moving at its own pace, available to be taken in at whatever depth the moment allowed. The sky continues. The nebula continues. The quiet is yours. Rest well. Before the full quiet settles, there is one more layer worth considering. The age of the universe, as best understood through observations of the cosmic microwave background and the expansion of space, is approximately 13.8 billion years. Written as a number, that is 13,800,000,000 years. The Helix Nebula's visible nebular structure is approximately 10,000 to 12,000 years old. Placed beside the age of the universe, the nebula's lifetime is so short that it would be invisible on any linear timeline drawn to scale. The Sun has been burning for 4.6 billion years. The solar system itself, the planets, moons, asteroids, and comets, formed from a collapsing gas cloud at about the same time as the Sun ignited. Earth, approximately 4.5 billion years old, carries within its oldest rocks minerals formed when the planet was very young. The star that made the Helix Nebula was probably born somewhere between several hundred million and a few billion years ago. It lived its main sequence life quietly, burning hydrogen in its core. It expanded into a giant. It shed its outer layers. And roughly 10,000 years ago, those outer layers were illuminated by the exposed remnant and began to glow. 10,000 years is a peculiar length of time from a human perspective. It is long enough to encompass all of recorded human history, the earliest writing, the first cities, the construction of Stonehenge and the pyramids, the rise and fall of every empire we know of, and still not be long enough to represent any meaningful fraction of the age of the Earth, let alone the age of the universe. The Helix Nebula has existed, in its current glowing form, for approximately as long as human civilization has existed in its current form. The two have, in a sense, been growing and developing in parallel, civilization expanding its reach and complexity on one small planet, the nebula expanding its glowing gas into a sphere 2 light-years across. Neither is aware of the other, except that we, a product of civilization, have turned our instruments toward the nebula and recognized what it is. There is no particular significance to this coincidence. The timescales are what they are. But it is a thought that sits comfortably in the mind at the end of a long exploration. The idea that while the arc of human history has unfolded on this planet, this ring of gas has been quietly expanding in Aquarius, illuminated by its dying star, waiting for no one, indifferent to observation, simply proceeding. And here we are, having looked at it together. The cosmos does not offer meaning in the way that stories do. It offers structure. It offers process. It offers the deep, patient rhythms of physics operating at scales that dwarf anything in human experience. Within those rhythms, the Helix Nebula is one brief, beautiful note. The expansion continues at 31 kilometers per second. The white dwarf cools by a fraction of a degree. The cometary knots drift outward. The photons travel. And somewhere on a small, warm planet, someone has been listening. Good night. The Helix Nebula has existed, in its current glowing form, for approximately as long as human civilization has existed in its current form. The two have, in a sense, been growing and developing in parallel, civilization expanding its reach and complexity on one small planet, the nebula expanding its glowing gas into a sphere 2 light-years across. Neither is aware of the other, except that we, a product of civilization, have turned our instruments toward the nebula and recognized what it is. There is no particular significance to this coincidence. The timescales are what they are. But it is a thought that sits comfortably in the mind at the end of a long exploration. The idea that while the arc of human history has unfolded on this planet, this ring of gas has been quietly expanding in Aquarius, illuminated by its dying star, waiting for no one, indifferent to observation, simply proceeding. And here we are, having looked at it together. The cosmos does not offer meaning in the way that stories do. It offers structure. It offers process. It offers the deep, patient rhythms of physics operating at scales that dwarf anything in human experience. Within those rhythms, the Helix Nebula is one brief, beautiful note. The expansion continues at 31 kilometers per second. The white dwarf cools by a fraction of a degree. The cometary knots drift outward. The photons travel. And somewhere on a small, warm planet, someone has been listening. Good night.